entonces necesito hacer escribir mis publicaciones para graduarme, terminar algunos experimentos para realizar las publicaciones y listo. Obviamente Claudia es mi tutor. Entonces hoy, aunque mi tesis tiene como 3 partes, yo voy a enfocarme en el fotosistema 1, porque es más relevante a este grupo. Los otros 2 partes son más relevantes a unos colaboradores que tengo en el proyecto. Y un punto que quiso hablar con ustedes. Esta presentación, el texto es puro inglés. Y la pregunta es si ustedes estarían bien si yo también hablo en inglés, porque inglés es el idioma más común para conferencias, publicaciones, entonces es muy bueno practicar la ciencia en inglés. Pero si alguien me avisa que hoy no, qué horror, no voy a entender nada, si es puro inglés, entonces yo puedo seguir hablando en español. Entonces, yo espero un momento, me avisa si inglés es imposible. If I continue in English, I will try to remember to speak slowly and clearly, and I'm very happy if anybody stops me and asks me to repeat something, explain a word, or explain something in a different way. Well, that's true in Spanish too. So right now, I don't think I have anybody saying that English is impossible. Okay, so I'm going to keep going in English, but you just stop me if it's not working, okay? So today we're going to talk about a few things. This part of this presentation is going to focus on a kind of spectroscopy that's based on Raman scattering. So I'm going to give you a very brief introduction to what Raman scattering is, and then a subsection of Raman scattering, which is a trick used using metals to give a surface-enhanced Raman scattering. And then I'm going to give a brief review of a paper that Claudia asked me to share with you guys. This is giving the paper itself is a review of some of the theoretical tools and models that have been developed to try to explain the mechanisms behind surface-enhanced Raman scattering. This is all relevant to this part of my project, which I'm going to talk to you about, which is a study of photosystem 1. I'll give you a brief overview of my project. I'll share some of my results, specifically the surface-enhanced Raman scattering results of the photosystem 1, future work and acknowledgements, as always. So what is Raman scattering? When you shine, sorry, that's not supposed to be there. My bad. Okay, so when you shine light at matter, it can interact in all kinds of ways, right? We're used to matter absorbing light, reflecting light, and it also scatters light. Most of the time, when you send a wavelength of light at matter, and this matter is moving around, it's stretching, it's bending, most of the time you're going to get what's called Rayleigh scattering. Rayleigh scattering is when there is a elastic collision between the photon of light and the matter and the molecule. So that means that the energy in is the same as the energy out. And that doesn't give us a lot of information about the molecule that our photon just collided with. Now, when there are bonds whose movement changes the polarizability of their electron cloud, that is how wiggly, how sloshing around, how much movement there is in the electron cloud, these are now what are called Raman active, and they can participate in Raman scattering, which is inelastic scattering. Inelastic scattering means that there is a transfer of energy between the two particles, the photon and the molecule, right? So it's possible that the photon coming out comes out with a higher energy, a lower wavelength. So this is called anti-Stokes. This is very uncommon. It's possible that our photon or scattered photon has higher energy, excuse me, it has lower energy and therefore higher wavelength than the incident photon, and that's called Stokes-Raman scattering. And that's the more common of the kinds of Raman scattering, of the inelastic scattering events. Now, I say it's more common of the two between Stokes and anti-Stokes because really the Raman scattering, this inelastic scattering event, it's very rare. It's about 1 in 10 to the 9 of these light matter interactions. Okay? So in normal Raman scattering, very weak signals. You need a lot of sample, and when you have bonds that are more polarizable, you're going to get more Raman scattering. So when we're looking for tricks of how to enhance the signal of the Raman scattering, we want to enhance the polarizability of the bond. We want to enhance the intensity of the laser light, the incident or the scattered light. These are what we're going to be looking for. So how have scientists done that? They've been developing this technique called surface enhanced Raman scattering. So again, we're going to shine light. In this case, this shined light is going to interact with a metal surface most typically. There are some semiconductors that are being studied, but very common to use metal, very common to use gold or silver. So you shine this light on the metal. Like all metals, there's a sea of electrons. And if you choose the correct wavelength of light, this is going to cause an oscillation in the sea of electrons, which causes electric fields on the surface. So the strength of this electric field is highest at the surface, and it decreases very quickly as you move away from the surface. So when we bring a molecule or a bond in a molecule close to the surface, it's going to experience this elevated, enhanced electric field, and therefore the Raman scattering is going to be enhanced. Another thing is that if the bond is literally in contact with our metal surface, this can participate in charge transfer events. And then this is going to increase the polarizability of the bond. And if it's more polarizable, it's going to be a stronger scatterer. So you're going to increase your signal. Another way to increase the signal is the orientation of the substance. So if the bond is its polarizability, the way that it stretches, if that is perpendicular to the surface, that's going to get an extra enhancement because it's going to have a stronger interaction with this electric field, as opposed to, say, a bond that's laying down and parallel to the surface. Okay? So the surface itself creates a field, an electric field, that is going to enhance the scattering. You want to be closer to the surface so you get a stronger electric field. You want to have ideally even like a chemical interaction with the surface to enhance further, and a good orientation. And this metal surface itself is important. Oh, excuse me. So of course, in my case, I'm going to look at photosystem 1, which is a huge protein complex. So if in this case, you might have your analyte, your molecule might be bigger, might extend further from the surface than where you have enhancement. Okay, so you might only see part of the molecule at one time. And then the surface itself, its shape matters and its relation to other surfaces matter. So for instance, here, this is showing that if you have a tip internal angle, so not just a flat surface, but a pointy surface, the pointier it is, the higher the electric field. And that's these blue lines here that are giving us this enhancement. Also, if you can put two pointy things next to each other, like this, the closer they get, the higher the electric field that's going to be formed right at their surface, and the more enhancement you're going to have. So we know that the geometry of the substrate also matters. Okay, so this is our very cartoon explanation of how this works, of how we're going to get information out of very small quantities of a sample. In this paper, they are doing a summary of, including 150 references, of the theoretical methods that are being used to try to describe the different enhancement mechanisms that there are behind SERS. Remember, because it can be from the electric field, it can be from charge transfer, it can be from the geometry of the substrate. Lots of stuff matters. Okay, so they're reviewing like literal mathematical models. It gets very complicated very fast. And they do point out that, you know, there's still a lot of discussion about how we should be modeling it. There's no one single model that is like cohesive, and there's still some work. There's quite a bit of work to be done here. And then I'm just going to point out, just because it's fun for me, Dr. Schatz, he was my general chemistry professor when I was in university, and he is awesome. He was very, very excited about science. Okay, so getting into this paper, this is another cartoon representation of what we were just talking about. We want to enhance Raman scattering. How are we going to enhance this signal that we get from the Raman scattering? We can increase the bond polarizability, and we can increase the electric field that is going to interact with the molecule. Well, specifically also with the incident and scattered light. So in this cartoon, this first one is kind of the least interesting in terms of enhancement. This is just pointing out that this dotted line, okay, so first here, this is our metal. Metals, as you might know, they have a valence band. This is where all their electrons are. They have a conductance band, which is empty, you know, orbitals that are empty of electrons, but an electron can come up here and then move around very freely. You'll notice that the metal doesn't have a band gap. That's why they're such good conductors of electricity and heat. They're showing here energy increases. This is the surface of the metal. On the surface of the metal, we have a molecule. The molecule has a highest occupied molecular orbital. It has a lowest unoccupied molecular orbital. And they're showing a dotted line with the omega symbol. This is representing the energy of our laser that we're going to shine on the sample. Okay, so this is the light that we want to interact with the surface, interact with the sample. It's going to scatter and it's going to give us information, right? So like some photons might be used to excite the surface, and then the next photon coming after it is what's going to scatter, for example. Okay, so this part here, this is just ground state chemical enhancement. And really what it's doing is there's an interaction between the metal and the molecule. And that interaction is going to change these energy levels. So the peaks, the wave numbers, the energy of the peaks of the SERS spectra are going to be a little bit different than the original Raman when there's no metal involved. Okay, so we don't have to worry about this too much right now. Moving along here, the second cartoon, this is talking about resonance Raman enhancement. So in this case, we're choosing a laser light that is equal to the gap in energy between the highest occupied molecular orbital, where the electrons are, the valence electrons, and the lowest unoccupied molecular orbital, where there's room for those electrons to be excited. So now we're going to use the laser. One photon of the laser excites the molecule. Now the next photon or photons coming up, those are going to then do the spectroscopy. They're going to be scattered. So why might this be helpful? If we put an electron into the LUMO, if you remember, I think you guys took general chemistry, and in general chemistry you learned that the different orbitals, whether it's in an atom or a molecule, are literally physically larger as they get up to higher and higher energy. They're less strongly bound to the nucleus, the center of the molecule. So if you're putting an electron up here in the LUMO, it is in a higher energetic state, and therefore it's less strongly held, so it's more polarizable, right? It's not so tight in. It's bigger and it's more amorphous. It's more polarizable. If it's more polarizable, we're going to get more enhancement. Okay. In this next cartoon, they're saying, what if we chose a laser light that was the difference in energy between the Fermi level of the metal and the LUMO of the molecule? So if the laser light is equal to this energy difference, excuse me, then what it can do is it can excite an electron from the metal into the molecule. So now what we're going to do is we're going to reduce our molecule, our analyte. Now we have, once again, an electron in the LUMO, and we just said that an electron in the LUMO is in a more polarizable state. And in general, now we have an excess of negative charge, and that excess of negative charge, an anion, is just more polarizable than a neutral particle. Okay. Now, finally, we have the plasmon resonance enhancement, and this is when we're going to choose our laser to have energy that is going to cause the electrons in the metal to oscillate, creating a localized surface plasmon that creates an electric field and gives us that enhancement. So this last one, they left it for last, but it is the most important, the dominant mechanism for the Raman scattering enhancement. Okay, so this last one here, that's what I'm talking about in this, just the very simple. Light shines, makes a plasmon in the surface. This generates an electric field. If you put an a molecule in that electric field, you're going to get enhancement of its incident and scattered light. So we get a stronger signal. Okay. I'm going to pause here and give you a minute if you have any questions while we're going. This is dense, I know, especially if you haven't studied this before. Okay. How are we doing? All right. Okay. So now let's look at some actual modeling that was done. I'm not showing you equations yet. We're easing into it. All right. So this is that last cartoon that we saw where we are choosing a laser wavelength such that its energy will resonate with the sea of electrons on the surface of our metal. So what have they modeled in this case? In this case, they're modeling a silver nanoparticle. So each one of these spheres represents a silver atom. And there are 20 atoms in this nanoparticle, and it's shaped like a pyramid. Okay? This is just modeling, right? All done on the computer here at this point. So now let's take a look at what's happening. This is telling us we're looking at the scale bar is for the strength of the electric field. Okay, red is low, blue is high. And in this case, when there's no resonance, so we're either not shining light on our nanoparticles or the light does not correspond to an energy that will cause resonance. Okay, and we notice it's between 1 and 4. And we notice, okay, the closer you are to the surface, the higher the electric field. This is something we've seen before. Now they run the model. We're going to look at the same particle. We're going to look at the strength of its electric field, but now we're shining a laser light on it at the appropriate wavelength to cause resonance. And what do we notice? Let's see if anybody is brave enough to talk? What happened when we added the resonance? Not a trick question. I see two differences between these two graphs. That's all I see.
There's a little more of blue color, and
Very nice. Yep, yep.
and the
So,
scale is changing. Before
oh
is
yeah,
1 to 4, and later is 1 to 150.
absolutely, absolutely. So we're seeing that the high intensity of the electric field it's a little bit like further from the surface of our nanoparticles, and the intensity of electric field is like almost, it's like what, like more than 40, more than 40, no, almost 40, excuse me, almost 40 times as great. Fantastic. So you add that resonance, you get almost a 40x enhancement of your electric field. And we've established that stronger electric field, stronger signal, right? Okay, now let's look at what they did. They took this sample, they took this theoretical nanoparticle in their computational models, and they said, okay, we're going to put a pyridine molecule on it, just simple organic compound, and we are going to model what it's going to look like. So here's the first spectrum. You'll notice that we have wave numbers down at the bottom. That's just energy, right? Low wave number, low energy. High wave number, high energy. Okay, and this is basically counts. This is how intense the signal is going to be coming out. So here they're going to model it, the pyridine on this compound, and we're using 514 nanometer laser light, does not resonate, and we get the spectrum. Then we're going to model it, but we're going to use 382 nanometer laser light. So we're using it with resonance. We're forming a plasmon, and we get this spectrum. And once again, what do we notice? You might say, no, look, it's the same. Like two peaks, two peaks. Okay, there's a big peak here. It wasn't there. I guess that one's a little stronger, but there's a big difference in our y-axis, in the intensity. So when you have a non-resonant condition at the bottom here, we're going from like 0 to 0.2. You add resonance, and all of a sudden you go from 0 to 2,000, right? So that's interesting. This is a theoretical spectrum, so they get to control what's contributing to the enhancement. They're not going to add in any of these other mechanisms that we're talking about. They're not talking about charge transfer. They have total control over the system. And something that I'm going to point out that I think is very interesting is we just said that you get almost a 4x increase in electric field when you get the resonance. But in the actual signal that comes out, you're getting more than 4x. You're getting like 10,000x, right? You went from like 0.2 to 2,000, right? So there's something happening. It's not like a 1-to-1 ratio. It's not double the electric field, double the signal. No, no, no. You get a huge return on that electric field, right? So again, we're shining laser light onto our surface. Some of those photons are used to excite the surface, creating a localized surface plasmon. That surface plasmon creates an electric field. That electric field interacts with our analyte, our molecule, pyridine in this case, and that's going to interact with the next photons that are coming in, new photons coming in. We've got incident photons coming in, scattered photons coming out. They're both interacting with the electric field. They're both getting enhanced. So right there, that gives us a hint on why it's not just a 1-to-1 here, because you get both in and out being affected by this electric field. Okay. How are we doing? Okay, let's be okay. So one of my favorite things was when I started to learn how to read mathematical equations in the context of science, right? So when you model something with math in science, it's telling you a story. And I think this is fantastic. So let's start with two equations that are basically the same, very simple equations from this paper. So we have a simple nanoparticle surface. We're going to put a molecule on our surface, and we have an electric field. This electric field can be perpendicular, and they mean like perpendicular to, or excuse me, this is parallel. This is parallel to like the axis substrate particle, like this here. So we're parallel to this line, that like the closest line connecting the molecule and the surface. And we can have same idea, but the other component of the electric field that is perpendicular, a little perpendicular sign, a little perpendicular to the axis between the surface and the molecule. Okay, so we have here, this is the intensity of the Raman signal that is coming from the parallel component, and the intensity of the Raman signal coming from the perpendicular component. And this here is the intensity, like the regular molecule Raman intensity, like no surface enhancement, times we've got this term here, which is the localized electric field parallel to the surface molecule axis. So basically this arrow here, or same deal, but perpendicular. So what can we say from this?
I think it shows like an increase in intensity.
Sorry, I got a noise just when you said.
Okay.
Oh, one more time.
That shows how intensity is higher or increases.
Increases
Because of the
depending on
electric
what?
field. The
Ooh, with the electric field.
Yes.
But the electric field, what, just straight up, linear? Or quadratic or cubic?
Times 4. I don't know how to say that.
Not elevated, yeah. So in English, we would say elevated or to the fourth power. So yeah, absolutely. This is huge. We have not just the electric field, but the electric field to the fourth power. So that's why in the previous simulations, you increase the electric field a little, but the intensity increases a lot, right? It has to do with the fourth power of it. So this is fantastic. All right, good. Now, let's take this very simple equation and see if we can make it a little bit more complicated, a little bit more detailed, see if we can get some more information out of this sucker. Okay, so we're now going to add another term. This is the distance between the surface and the molecules. So I'm just using this little blue line to try to show this. So we're going to have this distance here. That's what we want, or to the center. A lot of these simulations treat the molecules as a point charge. So, you know, they're all approximations, right? Only nature is real. Everything else is an approximation. Okay, so let's slap in some new equations. First of all, they're almost identical. Once again, they're almost identical. Let's see what's happening. So now we have the same term, the intensity of the Raman signal. It can be generated by the parallel electric field or by the perpendicular electric field. Now we're just going to say it's proportional, right? We're going to fudge it a little bit. So it has something to do with the overall polarizability of the system. Every time you see alpha, think polarizability. So now we're talking about how polarizable is this system in this parallel direction. Down here, we're asking, okay, how polarizable is this system in the perpendicular direction, right? So when I say system, I mean the nanoparticle and the substrate. Excuse me, the nanoparticle and the molecule. I apologize. Okay, so if that's what it's proportional to, let's break it out and, and we've got this Q of the molecule. So that's simply saying like a normal mode of the molecule. So it has to do with what kind of bond you're looking at. Are you looking at a carbon-carbon bond? Is it a single bond? Is it a double bond? All that stuff. So here, this has to do with the molecule. Now we're looking at the polarizability because it's alpha. M tells us it's the molecule. This term over this normal mode of the molecule squared. And now we've got this kind of complicated bit, right? This is to the fourth power again. So this is where we're talking about this localized electric field, right? This is what we're expanding. This is what we're expanding out, okay? So what do we see? We see contributions from the polarizability of the nanoparticle. That's our gold or silver. R cubed divided by R cubed. So this is, again, the distance between the surface. And down here in the denominator, we got 1 minus, coefficient. Now we got the polarizability of the nanoparticle and the polarizability of the molecule, once again divided by R, the distance. And it's not just plain old R, it's R to the 6th, right? So now just worrying about this part here, see if you can just kind of translate this equation. And really, I'm looking at this part here, right? Let's see if we can translate this part of the equation to tell us a story about what changes the intensity of the Raman scattering. So if we want to increase Raman scattering, what of these values do we want to be bigger and what ones do we want to be smaller?
I think distance to be smaller because it's
Mhm.
dividing the number. So
Yep.
a bigger number will be less intensity, I think. So
Yes.
with
Yep.
less
So if we,
distance,
yep.
there's more intensity.
Yep. So up here in the numerator, we have the distance between the molecule, the center of the molecule and the surface cubed, but it's in the denominator of this expression. So the smaller the distance, the closer we are to the surface, the larger this fraction becomes, which means the larger this whole term becomes, which is then in the numerator and elevated to the fourth power. So awesome, we want that. It also shows up in the denominator, right? So let's do our follow our logic here. If R becomes smaller, if this becomes smaller, this fraction becomes larger. And if we're doing 1 minus that, you wouldn't really know this, but this is going to be smaller than 1. So as this gets larger, it's approaching 1, which means this whole denominator is approaching 0. And as it approaches 0, the whole expression gets bigger and we get more intensity. So absolutely, we want small distance. We want R, the distance between our surface and our molecule, to be as small as possible. Anything else? What about polarizability? So if R is in the denominator and we want it to be small, then something that's in the numerator, we want it to be big. So the bigger the polarizability of the nanoparticle, the larger this sum, the larger the intensity of our signal. Down here, the larger the polarizability of the nanoparticle, the larger the polarizability of the molecule, the smaller this difference, the larger the intensity. Okay? And then, just to kind of emphasize that there's other things happening, if we look now not at the parallel, but at the perpendicular, what do we see? We see that this coefficient of +2, it's now -1. And we see that this coefficient of 4, it's now 1. So what effect is that going to have? So here, well, we're not making the numerator bigger. We're making it smaller. Oh, that's not good. The numerator gets smaller, our intensity gets smaller. Now here, instead of getting closer and closer to 1 minus 1, well, we're still getting closer and closer to 1 minus 1, but not as fast, right? It's not as fast. So again, this gets smaller. So the math is telling us that the electric field that's parallel to the nanoparticle substrate molecule axis is going to give us more intense Raman scattering compared to the one that's perpendicular. And the math also tells us that if we can increase the polarizability, we can increase the scattering intensity. That's the polarizability of our substrate, of our nanoparticle, and of our molecule. And I don't think I wrote it down, but if you can decrease the distance, you can also increase the scattering intensity. All right. One more. I'll go a little bit faster here. So this is talking about the charge transfer resonance enhancement. So this is that idea that if an electron from the, in this case, silver nanoparticle can be transferred to the metal, to the molecule, we can get some kind of enhancement. So I don't know if you guys have seen molecular orbital diagrams before, but they are fun. This diagram tells me a story. This story tells me that the nanoparticle, which is a pyramid of silver atoms, it has molecular orbitals with electrons, and it has a gap. So it's not just a normal metal. Now that it's a nanoparticle, there's a gap, right? That's different. If we have just a sheet of silver, there's no gap. Nanoparticles are weird. It's a metal, but it has a gap between the valence band and the conduction band. In fact, it's not even a band anymore. These are like discrete levels. These are discrete orbitals. And so then we have the highest occupied, lowest unoccupied. And this is pyridine. This is our molecule. Again, it has highest occupied orbitals and lowest unoccupied orbitals. And then the story of this diagram tells me that if I bring them together and I stick the pyridine onto the nanoparticle, now I have new states. I have a new state. All the energy levels have changed. I got the same number of orbitals, but their energy is different, right? So for example, it's a little hard to see because it's in a very fine pink. So try to get the angle right with your screen. But these occupied, highest occupied molecular orbitals of the pyridine, they come down here. They're still occupied. These highest occupied orbitals of silver, they come up here. They're still occupied. And then we've got this mixing of the orbitals that are unoccupied from the silver and from the pyridine. So these orbitals here, 1 and 2, that's the LUMO and LUMO plus 1 of the pyridine. It's still associated with the pyridine. What we're trying to show here is that because there's an interaction and influence from the silver nanoparticle, their energy level has changed. It's still localized on the pyridine, but the energy level is different. Okay? So they decided to do a simulation. They said, hey, what happens if we choose a laser wavelength so that an electron from the silver goes to the pyridine? Nope. Sorry. Okay, so that's the question. Now, over on the graphs, this is just plain old Raman that was calculated. This is theoretical spectrum. This is the only real experimental spectrum in the whole paper. And it's the pyridine on a roughened silver surface, silver electrode. Okay. So just real quick, we'll notice that you're not seeing all the peaks, right? It's not as much, or like, yeah, maybe they're there, but they're way in the baseline. Okay. This is the graph we already looked at. Okay, so this is with resonance, without resonance. And now we're choosing a third wavelength of light. This wavelength of 471 nanometers corresponds to an energy that's equal to an electron being excited from the silver HOMO to the pyridine LUMO plus 1. Okay. And what we're going to notice is that, well, the shifts are pretty much the same, but the intensities have changed. Now, instead of in all of these simulations and experimental spectra, this is the dominant peak right here. But now the dominant peak is this 1581 that corresponds to the ring stretch. So this whole ring stretching, and the 365, which is this whole ring twisting. So why would we have preferential enhancement of these two peaks? That tells us that the LUMO plus 1 orbital of this compound is in the ring. It's localized on this ring. So when we add an electron to pyridine, that electron's not hanging out on a hydrogen. It's not just on the nitrogen. It's not on any one carbon. It's delocalized around this ring. That's where the electron goes. Okay. So that sounds kind of esoteric, but if we wanted to have information about what parts of a molecule are involved in electron transport, that might be useful to know. So that if you're designing new molecules for your solar cells to be electron transport materials or hole transport materials, you're saying, okay, so when this gets reduced, where is that electron going? How can I make that function? I want to preserve that functional group going forward. I want to try add more of that functional group moving forward. Okay. And that's really important for a different part of my thesis. How questions on this paper? Good Lord, I've been talking a long time. Yeah, I didn't even show you the tensors and everything. It's just, it gets to be too much. It's honestly, I haven't studied enough math to fully understand this paper. Maybe some of you guys would be able to read some of the more complicated equations better than I can. But I do encourage you, as you're reading papers, as you're studying stuff in class, try to let the mathematical equations tell you a story. It's a very concise, very beautiful way to convey information. Okay, so what is this part of my thesis about? I want to study the electrical properties of a single or few low number of photosystem 1 complexes when you can put them between nanoelectrodes. Why? Because in this group, we like to try to make solar cells using photosystem 1. And that means that you need to move electrons around with the photosystem 1. So why not study it on a very small scale, see if we can get something interesting. So the first challenge I had to do was to figure out how to use dielectrophoresis to physically manipulate the location of the photosystem 1 so it would go in between nanoelectrodes. I don't want to just wait hours and hours hoping that Brownian motion walks into nanoelectrodes. It might take years for that to happen. So we gotta direct its motion. Then we can measure the current voltage curves. And this was really interesting because in the literature, when they show this, it looks just like a conductor, like it just goes in a straight line. It goes the same if it's negative voltage or positive voltage, doesn't seem to matter. When I measured this, I saw that in one direction, we got current. If we try to move the electrons in the other direction, not so much, or no current. This is basically within the uncertainty of the measurement. So these are all basically zero. And not only does it seem to have a single, it could be directional dependent, which is what we expect from nature. Like photosystem 1 is supposed to take electrons from one side that it receives from a protein, excite them by absorbing light, and spit out these excited electrons on the other side to another protein. So it's only supposed to go in one direction, which is what I see. And it's got this weird shape to it. This shape looks more like a diode or a semiconductor. Maybe this could be used as a transistor. Oh, this is the control. This is just using the buffer, right? So if you just have a salty solution, nothing's really happening until you get to kind of higher voltages. Maybe it's getting above zero. So if it looks to be direction dependent, then maybe I have a specific orientation of the photosystem 1 in that nanogap. So how can we try to figure out the orientation? Well, maybe we can use SERS. We know that the part of the photosystem 1 that is in direct contact with a gold nanoelectrode is going to have the highest enhancement. So let's see if we can look at some of that. First, just because it's fun, dielectrophoresis is when we exploit non-homogeneous electric fields and the movement of polarizable particles through them. You control for the particle and medium dielectric constants. You got to tune to the correct frequency of the applied alternating current, and then you can move it around. So this is a microelectrode. Not too interesting. The interesting part is this shape here. This is one nanoelectrode. And over here, this is another nanoelectrode. And right there is the gap. Okay, there's a tiny gap there, a few nanometers. So this is just an optical microscope. You're seeing the refraction. These are about 300 nanometers wide this way. So you're seeing the refracted light on those nanoelectrodes. So I'm just going to go ahead and put little lines there to remind you where it is, because when we go to the fluorescence mode of the microscope, can't see it. All right, so first thing we're looking at is these little fluorescing particles. That's photosystem 1. And you notice a lot of Brownian motion, just random movement, random movement. Then I'm going to turn on an AC field across this pair of electrodes, 20 volts and 1.7 megahertz. And like instantly, as soon as I turn that on, a photosystem 1 that was kind of up above this electrode swoops in and goes right to the nanogap. So I had to figure out the conditions to get that right. And then when I started to realize that there was this orientation, I started concurrently applying a direct current across that gap to try to orient the photosystem 1. And then, so we can do electronic measurements, and if we take it over to a spectrometer, we can get spectroscopic evidence. We can see what it looks like. So if you recall, I said in my earliest cartoon that if you have a really big analyte, you're not going to see the whole analyte. Only some of it is going to get enhancement. And obviously, the closer to the surface it is, the more enhanced it's going to be. And what I'm showing you here are just kind of, I picked out 3 spectra from, this is from one time series, and this was from a different time series, but the same spot. I just opened and turned off and on the time series. And what we notice is there's a lot of change. So why is this thing changing so much? I think it's because it's moving. So we got this big photosystem 1. Thing's enormous. It's like 9 nanometers thick, and it's like 9 nanometers this way, 35 nanometers that way. So if it's moving at all, parts are going to be coming in and out of contact with the surface. The angle that our functional groups are with the surface is going to change. So they're going to become more or less enhanced. And the regions that are going to be in the hotspot, in the enhancement region, are going to change. So that's, I think, what we're seeing here. We're seeing like sometimes peaks are less or more intense, or they're so weak that you don't really see them, all throughout. All right. So comparing to literature values, we can hope to identify what these peaks correspond to, what physical parts of the compound there are. So for instance, kind of in the center of photosystem 1, we have this active center that is taking the electrons, and there's redox centers, and it goes through. So electrons would flow this way. And so they have what's ultraviolet resonance Raman. So this is specifically resonance Raman. They're picking up where photosystem 1 is going to absorb light, like we showed you in the earlier cartoons. And then they get the spectrum out. So yeah, maybe there's some overlap. Maybe some of these peaks have to do with they're assigning these to specific amino acids in this core, right? Because in this case, they just looked at the core, at the cofactors in the core. So if we're seeing the core, why don't we see all the peaks? Well, we expect that in resonance Raman, some peaks are going to get extra enhanced. We're not doing resonance Raman up here, certainly not the same kind of resonance, right? We hope to see alpha helices, because if you look at the structure of photosystem 1, it is like 51 alpha helices, especially around the belt area. They're all over the place. So from the literature, we expect to see the alpha helix secondary structure shows some like typical features. There's amide bands, amide 1 and 3. There's the CC carbon-carbon backbone stretching is different for an alpha helix versus when it's not in an alpha helix, for example. And we look and we say, well, maybe, well, maybe here, maybe we've got the amide 3 band. Maybe one of these peaks is the amide 3 band. There's random coil. It's this gray part that you see below and above. There's some random coil in the middle too, but it's mostly above and below. And so if we're seeing like extra random coil strength, then that would indicate that either the top or the bottom is more in the hotspot as opposed to it laying on its side into the hotspot. We say, okay, maybe we've got the amide 3 random coil band in here. Maybe that's the amide 1 stretch. Beta sheets, not a lot of beta sheets happening, but there are a few on the top and a few on the bottom. So if we have, in some trapping conditions, if we see extra expression of beta sheets and random coil, we would expect that we could interpret that as, okay, now we have either the top or the bottom in the hotspot, preferentially over the side, for example. And just other things that might be able to be identified, like CN stretching here. That looks, it's in the range that's found in the literature. But the big thing is there's a lot of peaks, there's a lot of information. And as we saw, when the photosystem 1 comes in contact with, in this case, gold, there are going to be slight changes in the energy levels, which means that the wave numbers here of certain peaks are going to change a little bit. So if it's a bit different than the literature values, we can explain that. It would be great to model this, but it is huge and therefore hard to model because it just takes a lot of computational power. So I need to deconvolute a lot of those peaks, because you can see like, oh yeah, there's at least 2 here. Maybe there's a shoulder there. Maybe that's another peak. This is obviously at least 1, 2, maybe that's more, maybe that's noise. So deconvolute the peaks. I'm going to do some of these current voltage measurements at a low temperature, hopefully, because if the current drops to 0 when you're below 20 degrees Celsius, that indicates that your mechanism is tunneling. But in nature, and that's what's been reported. That's what's been reported in other studies for a single photosystem 1. But if what did I just say? If the current drops to 0 when you're at low temperature, if the current drops to 0 when you're at low temperature, that means your mechanism is hopping because there's not enough thermal energy to help the electrons hop from redox center to redox center. If the current is unaffected by temperature, then it's tunneling. And having the current be unaffected by temperature is what's been reported in a paper where they were studying single photosystem 1. So they were observing tunneling, which is not the known natural behavior of the compound. Can't do this without the support of Claudia. This data came from my stay in Taiwan in Dr. Jiafu Zhao's group. His students, Katrin and Gerhard, helped me a lot. And Leo from UCR, he's also in this project, which is funded by the US Air Force Office of Science Research. So if there's any questions or comments, I'd be very happy to talk about it. Or if you want to see something again, hopefully all the slide numbers were visible. All right. That's all I've got. I don't know if there's any lab business that people want to address.
Jessica, I don't know the others, but I just want to say it's like a huge investigation. It looks like so amazing. And I don't know, just congrats for just the process and hope reading more about this in the future.
Oh, thank you very much. Thank you very much. Yeah, it's definitely a challenge. I have started to, like a mantra, like a thing that I repeat to myself a lot that you might find helpful, is I say, whenever I go into an experiment, I say, this experiment is probably not going to work the way I think it's going to, or if I'm feeling more negative, I say, this is going to fail, but I'm going to learn something, so it's okay. So as long as, whether or not you get the results you think you're going to get, whether or not you run into a problem you didn't anticipate, if you learn something from it, you're moving ahead, and that's the important thing.
That's a really good mantra.
It also means that you need to measure stuff carefully, like if you're making a solution, make sure you know what the concentration of that solution is, because if you're like sloppy about it and then something's weird, it's not the way you expected, you don't know if it's because the solution was what you thought it was or not. Does that make sense? Like if you're sloppy, you can't learn from it. So you got to be careful. And then whatever happens, you can learn from it.
Yeah, that makes sense.
Yeah.
Thank you so much.
Thank you guys for listening. Kind of a long one. Thanks for your patience. All right. Well, have a great day.
Have a great day, you too. Bye-bye.
Ciao.
Bye.